Good morning, everyone. Welcome to our pre-lab lecture. Today we are going to continue with the discussion on chapter 3. We will move on to chapter 4 next Tuesday if we get done with chapter 3 today. Mark your calendar next week, Thursday, will be our midterm exam number 1. More information will be shared through Canvas by tomorrow. I always give you the study material, and you have 1 week to prepare for the exam. So tentatively, next Thursday will be our midterm exam number 1. More information will be shared. Last week, last Tuesday, this past Tuesday, we went as far as section 3.4, and we looked at the concept of determination of molar or formula weight of compounds. All right, I brought to your attention the difference between molar mass and formula weight. When you are asked find the formula weight, that means you take just the formula of a compound, or could be ionic compound or formula for molecular compound. Still the same concept of using the periodic table. Here is on my whiteboard, here is phosphorus trichloride. By now, you should be able to interpret the periodic table, identify the atomic mass of each element of the periodic table, and you have to do. We solved this problem on the PowerPoint slide, chromium 3 sulfate. I showed you how to use the crossover rule, which we learned earlier on. With the polyatomic ion, you should know the ionic charge for the sulfate and also other common polyatomic ion mentioned in the text. Here is there are two ways you can be tested. Either you are given the chemical names and you are expected to translate to chemical formula so that you can relate to atomic masses on the periodic table, or you are given the chemical formula and you ask is just to look at the periodic table and add the atomic masses of elements involved in the chemical formula. It's straightforward. I'll give you the periodic table, okay? Let's see, having gone through the determination of the molar mass of a compound, it is tied up to percent composition. Percent composition is simply the mass of the component. We can loosely define that as mass of, all right, percent composition is given by the mass of element. In this case, if you are given the compound of mass of compound times 100%, times 100%, it is the mass of the element of the compound. At the top here, it depends on how many elements or how many atoms of that element you are dealing with over the total mass or the molar mass of a compound. For example, here, if we have H2O and we are asked to find the mass percent of hydrogen, all right, mass percent of hydrogen, for example, in the molar mass of H2O, given that this is the molar mass of H2O, 18.02, remember it's grams per mole. Look at how many hydrogens we have. 2 hydrogens. You multiply by 2 the atomic mass of hydrogen. This is the atomic mass of hydrogen, 1.01. This is of the periodic table over 18.02 grams times 100%. This is what you will do if you are asked to find the mass percent of hydrogen. So 2.02 divided by 18.02, 11.15. So this is 11.15%. All right, 11.15%. If you have two, all right, if you have two elements in a compound, you can subtract from 100 to get the mass percent of the other. In other words, mass percent of oxygen. From H2O, we can subtract 11.15. It's the same thing. 88.85. Sometimes mass percent because of the decimal places on the of atomic masses might be 99.99% or 100.09% because the atomic masses always have places of decimal. So you may be given the atomic mass of a molar mass of a compound, or you may be required to use the periodic table and calculate. Yes, Jason, we are around there in the text. Read the relevant. Whatever we'll stop today will be included in the test, but whatever we'll cover on Tuesday will not be in the next test, but it will be in the quiz and the upcoming exam. So you're right. Whatever we'll stop today, Jason, will be in the test. So going back to atomic mass percent, this is just illustration. I've just given you example on how to determine the mass percent of an element. In this case, the formula mass of a compound can be given, or you may be required to use the periodic table times 100%. Since I had two elements in H2, I had to subtract 11.15 from 100 to get the mass percent of oxygen, to get the mass percent of oxygen. If you have three elements in a compound, you may be, all right, you may find the mass percent of the two and then subtract from 100 the sum of the two. Still, it will work. If you have three elements, you can find the mass percent of the two elements and find the sum of those, subtract from 100 to get the mass percent of the third element. Glucose, it is just assumed that you know the formula for glucose. Will be given that, and in glucose we have carbon, all right, oxygen, and hydrogen. This means there are 6 for glucose. There's 6 carbons. Therefore, this is the formula weight for glucose, 180.0 AMU. There are 6 carbon atoms in glucose, and this is the mass percent of oxygen. So we are looking for only oxygen. We find the mass percent of it. Any question on the mass percent composition? There are a couple of problems at the end of the chapter you can practice with that. I won't be able to go through all or extensive examples on mass percent concept. Let's see the Avogadro's number. This is Avogadro's number is a number used by chemists, all right? It is a number used by chemists to express or to represent what we call a mole. Avogadro number represent a mole of anything. MOL is an abbreviation for mole, all right? Of anything contains this number, and we call this number Avogadro number. This is Avogadro number, and chemists use this symbol to represent Avogadro number. Next time you see Na, uppercase Na as a subscript, with N, it's represent Avogadro number, and we call this, or it represent 1 mole of anything, okay? We have Mole Day, all right? Mole Day is not like a public holiday. Every 23rd of October, you see this? Every 23rd of October, from 6:02 a.m. to 6:02 p.m., you know, that's a Mole Day. I've seen T-shirts from American Chemical Society having the theme of moldy. 602. So here, this is a single molecule of H2O, a single molecule of H2O with oxygen, red, hydrogens being white spheres. We will see this in chapter 8. If this is a single molecule, if we have Avogadro number, this number of this, if we count 1, 2, 3, 4, all the way to this large number, exponential 23, we have 1 mole of, all right, 1 mole of H2O. And this mass you see here represent the mass you will see on the scale. So if this is my scale, this is my calculator, assuming that I can count the number of water molecule, 1 to all the way to a Avogadro number, the scale will read what? Will read 18.0 2 or 18.0 to 1 place of decimal. It will represent 1 mole, which means I can derive an equivalent statement using H2O. 1 mole of H2O, all right, contains, this is molecules, times 10 raised to 23. I'll say molecules of H2O, and it weighs 18.0 grams of H2O. Take home message here is 1 mole of anything, let me abbreviate that, equals to Avogadro's number times 10 raised to 23 molecules, which is equals to molar mass, or formula. Let's just say formula, molar mass. It's molar mass. Sorry about that. It's got to be molar mass because of 1 mole, molar mass. If not given, you get this from what? From periodic table. You get from the periodic table. So I don't have to, you know, if I'm not even given, all right, if I'm not given the number of, number of molecules or atoms, if I use the periodic table, okay, I know that 1 mole, anything on the periodic table, if you add the atomic masses, we talk about the mole, which is the Avogadro number. This is Avogadro number. and we talk about atoms or molecules. Specifically here, molecules refers to molecular compounds. I use here molecules because it is a molecular compound. It's the same thing. I have ionic compound, you know what ionic compound is? Let me relate this to the terms. There are some terms used which you may think that it means something different, but it's the same thing. All right. PT stands from the periodic table. Maybe I should be writing this stand for the periodic table. Oh, Isabel, this is periodic. Yes, you get the lower part from the periodic table. Now, I was talking about the terms you may come across in the problems, and this has to do with the ionic compound. We say 1 mole of let's say sodium chloride contains Avogadro's number of, you will see now the term will change to atoms or formula unit, which is equals to molar mass of sodium chloride. The formula unit here you see refers to ionic compounds. We use atoms or molecules. Now, the word atoms here is when you are representing an element. For an element here, an element that is just an element of the periodic table. 1 mole of Na, it's not NaCl, contains 6.02 times 10 raised to 23 atoms. You see, this is just changed now to atoms because you are looking at one element equals to atomic mass. In this case, for sodium, it's 22.9898. I'm getting this from the periodic table, and this is grams because I have Avogadro number of atoms. It will weigh whatever we have. So the terms used along with this depends on whether you are dealing with an element, and then you talk about atoms. If you are dealing with ionic compound here, sometimes maybe formula units or particles. Sometimes they use particles or formula units. And then for molecular compounds, they use molecules. So molecules for molecular compounds, particles are ionic compound. Now, we will switch gears now to using grams per mole. When we say now molar, it comes from the word mole, and we know what mole is. Wherever we say molar mass, we are referring to Avogadro number of things, and the units is in grams per mole. When 1 mole of, that means Avogadro number, we use the grams per mole. But for formula mass formula unit, we use the AMU. So formula weight AMU for the formula of a compound, whereas the molar mass is grams per mole. It has the same numerical value, except for molar mass, we use grams per mole, which means when you say grams per mole, you cut Avogadro number of items. Look at this diagram here. Look at the picture. And let's see if we can relate to molar mass. What this means is 1 mole of H2O. This is in graduated cylinder. If we have 1 mole of H2O, that means Avogadro number of molecules of H2O, it will weigh 18.0 2 grams. And how do we end up with that? Just adding the atomic masses of 2 hydrogen, 1 oxygen adds up to that. 1 mole of sodium chloride, 58.45 grams. Don't memorize these numbers and think that, how did we end up this? Do we really need to memorize? No. It is just the concept that you are given the atomic mass of sodium, atomic mass of chlorine. This is from the periodic table, by the way. And then you add the 2 atomic masses, gives you 58.45. That's where the numbers are coming from. For oxygen, 32.02 is from the periodic table that you have 2 oxygen. So atomic mass of 1 oxygen, add another oxygen, that's where 32. So if I'm given the chemical formula of any compound, and then I can just use the periodic table and find the atomic mass of that. All right. I don't want you to just try to memorize things around. It will be complicated if you are given any other chemical compound. Any question on determination of molar mass and how it relates to Avogadro number? Look at this on the table 3.2. This is just an example on how the Avogadro number is related to the molar mass of the compound. If you look at this AMU, it means the formula unit. This is 1 nitrogen, same numerical value. That means we have 1 nitrogen. But here 14.0, that means you have Avogadro number of hydrogen atoms, same numerical value, but it is grams per mole. That means 1 mole of nitrogen atoms. Instead of saying 1 mole, I can say Avogadro number of what? Nitrogen atoms. So when you see these numbers here, and these numbers just looking the same, like exact, and you're wondering what's the difference between this and that is, you count only 1, but here you have Avogadro number of those things. That's what it means in terms of the difference. Here, you may ask yourself, what is the difference between the silver ion and just a neutral silver atom? Even though we remove an electron or an electron is missing in here, all right? Even though 1 electron, we'll see later on how cation is formed by removing an electron. Doesn't change the formula weight or atomic mass, because that 1 electron is 1,800 times smaller, so it will not change any mass of those elements. It's just like having an 18-wheeler truck, all right? Having an 18-wheeler truck on a scale and then a mosquito just patch on top of it, but it's not gonna change anything. That's what it means by that. So for an element, we talk about the atomic mass. An element, this is just of the periodic table. We use the formula unit. Where we are going with this now is, all right, where we are going with this right here, look at what I'm circling on my whiteboard. What I'm putting in the box is, we can now use dimensional analysis to convert between amounts. Which amount? It could be finding the number of moles, finding the number of molecules, or finding the mass. This is an equivalent statement right here where you need to derive the conversion factor to change from grams to what? To moles. Use the molar mass, and you can find this from the periodic table. Or if you are given the moles and you want to change to formula units, and when we say formula units here, this refers to ionic compound. We use Avogadro number. We use Avogadro number. Caroline? Yes, means positive. 1 means 1 electron is missing, and when there is an overall charge of negative, means one extra electron has been added to whatever you are looking at. So if you have an overall charge of +2, that means two electrons are missing. If you have an overall charge of -3, means 3 extra electrons have been added. Remember, from subatomic particles, electrons are negatively charged. No, exam will not be open notes. No. It's gonna be proctored. More information will be shared, Tony. It will not be open notes. All right, so coming back to PowerPoint lecture here, the slide you see here is just a roadmap on how you navigate a given problem using the conversion factor. Here is an equivalent. I may give you in an exam this number I will give you, but you are expected to know how to change from moles to formula units using Avogadro number. Avogadro number is what you have here. You may have a setup, all right, but somebody will have difficult keying in these. Like they don't know how to use their calculator to write the exponent. How do I need? You need to know your calculator. If it is TI 31 or 34, you have to be able to use or express this number in scientific notation. So Avogadro number. Maybe once we solve one problem, you'll see how to convert. This this is relevant in the sense that we'll have to use this when we are converting from moles to atoms. For example, how many atoms are in 3 grams of copper, 3 grams of copper. This at the outset, you are expected to use or understand that 1 mole, all right, 1 mole or 1 mole of copper contain Avogadro's number of formula units or atoms, which is equals to, I'm just going to look at periodic table, 63.55. This is 63.55 grams. I'm just synthesizing the information. Where am I getting this? I'm deriving from the fact that I should know what a mole is in relation to the atomic mass of an element. Here you gotta change, all right? I'll recommend that you write down if you don't know what you are looking for, how to set up your problems, write what you are given. We are given 3 grams of copper. Whatever you want to get rid of here is grams of copper. You are looking for atoms. So atoms at the top right here. And the equivalent statement we need to use is this portion, that portion. So set up your problem in such a way that you plug in the values 5, 5. And then this is Avogadro number 6.02 times 10 raised to 23. And then grams and grams will cancel. You'll remain with atoms. Will remain with atoms. Trust me, somebody can have set up the way I have on my whiteboard, but the problem is when it comes to using the calculator, how do you key in? All right. So if I were you, I should have my calculator right now. And then you see you are going to get whatever the value I'm getting times 6.02. Second function, this is 23, all right, divided by 63.55. I see here this is 60, not 60, but 2 point, yeah. I see this is 2.8 times 10 raised to 22 atoms, 22 atoms of copper. 22 atoms of copper. This is the numerical value. Please, you'll have to set up your calculation. I know somebody will have difficulty, keying in on a calculator. You can just multiply across and divide by that, or you can divide this and by that to get the answer. So know how to set up your problem in such a way that you end up. If I look at this, it might look scary to some of you, but if you have in a simple fashion and sees you still the same thing. For one significant figure, because of one significant figure, I guess 3 pointed, making that 3 significant figure. 3 times 10 raised to 22 atoms, or this is one figure, one significant figure. So we have used what? We have used the Avogadro number to move from grams to formula units, or grams to atoms. Any question on that problem? You'll see this in the next exam or this coming exam. You'll see in the quiz. You'll also see in the homework how to do the conversion from atoms to grams or grams to atoms. I think we will come back to this empirical formula later. Let me just solve this one more example. Before we come back to empirical formulas, let's see this example on converting between moles and grams or grams to molecules or moles. Calculate the following quantities. A mass in grams of 0.105 moles of sucrose. In this case, you are not given the molar mass of sucrose. I know some of you, if it was homework assignment, you'll just Google out molar mass of, and then write down the formula. But if you are not given the molar mass, if it was face-to-face lecture, you are given the periodic table, and this is the problems presented. How will you navigate that? With this, the hint here is you need to find the molar mass of sucrose. Molar mass of sucrose. And it turns out that 1 mole of sucrose equals to 6.02 times 10 raised to 23 molecules. I know it's molecules because it's non-metals, equals to 342.2 grams per, let me just not even put per mole because already we have mole. That is the statement I should have, or I should write down. And here it is a question of moles and grams. So if it is moles and grams, I will relate this and this right here by saying 1 mole equals 342.2 grams. So that in your setup, write down what you are given, 0.105, and I see it's 3 significant figures, mole. I want to get rid of what? I want to get rid of mole here. I'm looking for grams at the top, The numbers will come from here. This is where I'll get the numbers. 342.2, 343.2, and this is 1 more. mole and mole will go away. You multiply that by, all right, 342 342.2 times 0.105 and 335.9 grams of sucrose. I've changed from moles. Mass in grams of 0.3 significant figures. The key here is, using the knowledge we learned previously. This is what? This is the chemical formula. Will you be given the chemical formula? Yes, in some cases. Some you may be required to use the knowledge we learned previously in chapter 2, writing the correct formula for either molecular compound or ionic compound. Sometimes you may be given the molar mass, such as 342.2 grams, you may be given, save time. I look at the problems and give you extended time if you are to use the periodic table. I have to account for time on how to find the molar mass of this so that you have the correct value. So here you are given the formula. But in B, if you look at B, you are not given the formula for the ionic compound. This will call for, or you are expected to translate the chemical name to chemical formula. Ammonium phosphate, this is ammonium. Ion, it is a positive. And then this one, how do I know? You should be able to write the formula for phosphate. You see, this is a problem of its own, that there is the writing of the correct formula for ionic compound, then you find the molar mass. So if you don't know how to write the formula, correct formula for ionic compound, or any compound for that matter, then we are in trouble. If you don't know how to write the formula and you don't know how to find the molar mass, then we are in trouble. So with this is the formula for ammonium phosphate. The 3 is coming from phosphate, and then this is the correct formula for ammonium phosphate. And then from here you can use the periodic table to find the molar mass, and you can Google out, or you can use the periodic table to get that. I don't recommend Googling out. Sometimes they give you wrong values. Use the periodic table, and turns out that this is the molar mass of ammonium phosphate. We haven't solved the problem. So if you look at this, you have to translate this to chemical formula. If you don't know the formula for ammonium, if you don't know the formula for phosphate, this is polyatomic ion, then you'll not end up with the correct formula, and then the formula molar mass will be different. So with that, 1 mole of NH4 3 PO4 equals 6.02. This is 6.02 times 10 raised to 23. This is particles or formula unit, and it weighs 142.09 grams of ammonium phosphate. Now we are looking for what is the mass. So the mass, that means we're gonna use this right here. And I'm given the number of particles. So the equivalent statement we will use is this, 6.02 times 10 raised to 23 particles equals to 142.09 grams of, all right, of ammonium phosphate, NH4, 3PO4. This is the equivalent statement we need to use in B. So I'll write down what I'm given. Just like I said before, some folks may have difficulty handling this using, and I see three significant figures, times 10 raised to -3, all right, because of space. I'm looking for grams of NH4, 3PO4. This is 3 there. Atoms. At the bottom is the Avogadro number, 6.02 times 10 raised to 23, and here mass of ammonium phosphate 142.09. I used the periodic table to find 142.09, that is the molar mass of ammonium phosphate, so that atoms and atoms will go away. We have atoms here. The next
Can you
is,
go over the molar mass really quick? Because I got 149.
Is it 149?
That's what I got when I rounded it.
That's what I got too.
Oh yeah, 149, you're right, yes, you're right, 149. This is 149. Yes, 149, you're right about that. And then you plug in that 149 using the periodic table, right?
Yes.
Yes, thank you, 149 for that. So if we have to, this is where the challenge comes in. Handling this using your calculator, please learn how to key in the exponent. Go to TI support session, I mean support session. Let me know if you are not getting the right answer, how to key in, because the functions on the calculator varies from calculator to calculator. I'm using TI-83 plus. So you may want to use parentheses, all right? Some folks may key in the way it is and they don't get the right answer. So 2.2.50 to -3. All right, -3, let's all do it together and see, times 149.09 divided by Avogadro number, 0.02 exponential 23. And here we got, I got 6.19 times 10 raised to -25. This is grams of NH4, 3, PO4, like that. Three significant figures, anything on the multiplication sign. So this is an example on, a compound problem that you are also being tested on how to use the periodic table to find the molar mass of a compound. That's a concept of its own we learn, finding the molar mass. And then there is also the concept of writing the correct formula for what? For ionic compound or molecular compound using the prefixes. Any question on the molar mass, changing from moles to atom, the key thing is understanding, let me wrap up this. The key thing is understanding this. Look at this. If you are dealing with an element that is of the periodic table, and if you are dealing with the compound, one mole of an element equals 6.02 times 10 raised to 23 atoms, which equals to atomic. This is just of the periodic table. This is from remember, this is just an element on the periodic table. But a compound is when you put two or more elements together, such as ammonium phosphate. You saw how we constructed the chemical formula, how we wrote it down. In this case, 1 mole equals to Avogadro number, molecules, or particles. Sometimes they use particles, which is equals to molar. And you know how to find this from periodic table,
Professor, I had a question about the last problem.
Yes.
Do you mind going back on your whiteboard?
All right, here?
Yeah. Wouldn't we? I thought we wouldn't divide by Avogadro's number since we're not converting it to atoms.
Oh,
Like,
we are looking for what? We are converting to grams. Look at the problem. If I understood well, what is the mass? So the final answer should be in grams, right?
yeah.
So the molar mass is right here. Look at the right. And the Avogadro number is below here so that we reconcile atoms and atoms. You see how I'm canceling out atoms and atoms?
I thought we started with moles though. I don't think it.
Oh yeah, moles, grams of 3 moles. Molecules. So if we have moles here, if it is atoms, yes, you're right about that. If we have 2.3, it's the same thing. 2.3, what? 2.35? No, 2.50 times 10 raised to negative 3 moles. Yes, over that. 149.09 grams of 1 mole of ammonium. So if we have this for moles, NH4 3 PO4, so that 1 mole and 1 mole will go away. So we are using, if you are given the mole, yeah, you are mole for that, we use atoms in the first one, but for these moles will be 2.5 raised to negative 3 times 149.09, and that is 0.
I got 37 grams.
Yeah, 7 and 3 grams, that means 3, right? You got this?
Yes.
Okay, grams of NH for the formula for that 3PO4. Now, yes, this is in line with the one we have here. And going back to this, I assume that this was molecules. If we have here as molecules, this is more. So the correct answer for this B is this. But here on my whiteboard, to be clear, the one we see, where is it? Here is, if we assume this was right here, I made mine to be atoms or molecules.
Thank you.
Yeah. So if you are given here as molecules, MOLEUs molecules, then this will be the correct answer. But as far as the PowerPoint slide is concerned, And then using strictly the mole here as for mole, as in this, and then we'll use the what? The grams. It can, in these problems, in this dimensional analysis, it can go any way. You can be given the mass and you are asked to find the moles. You can be given the grams and you are asked to find the molecules or atoms. So,
will you be spelling out molecules in the problem, or
yes, it
just
will be spelled. Yes, it will be spelled so as to avoid confusion for that.
Okay, cool.
So it can go either way. So let's go back to, there was the concept, I skipped the empirical formula of compounds, and just this is a different ball game altogether. Before we solve problems on empirical formula, there is empirical formula is simplest whole number ratio of atoms in a compound. It is a whole number ratio, all right, empirical formula. I will be using this abbreviation for empirical formula, EF, which is simply the simplest whole number ratio in a compound. Uh, in chapter 1, I believe, we looked at how to write the empirical formula from the molecular formula, such as benzene. If we have C6, H6, to give you an example, the empirical formula is CH, dividing it both sides by 6 to simplify to the simplest ratio. This is nitrogen, dinitrogen, tetroxide. Empirical formula is NO2, nitrogen dioxide, the laughing gas. I'm just writing the simplest. What you see here is empirical formula. We looked at this before, just simplifying, but we can calculate the empirical formula using the masses of elements in a compound, or percent, all right, or percent composition of a compound. Percent composition of a compound. Now, it is assumed that whatever the percent you are given, all right, whatever percent you are given, it is assumed to be the masses of that compound. For example, here we have 61.3%. It's assumed that this is the mass of carbon. So 61.31 grams of carbon. Hydrogen, 5.14 grams of hydrogen. Nitrogen, 10.21 grams of nitrogen, and 23.33 grams of oxygen. Always the percentages should add up to 100. You may have 99.99, it's okay. You may have 100.01, a little bit or a little less than 100%. It's because of the places of decimal on the atomic masses of element when they calculate the mass percent, and round off either to 2 places of decimal. So percentages always add up to 100. If you are given the percent of the first 2 or first 3, and you're missing, the mass composition of the third one or the last one, you subtract from 100. If you look at what I've just done with the mass composition, I translated that to what? To grams. Then in determination of the empirical formula, you have to find the number of mole or atom or moles of each element. For carbon, see 61.31, all right, 61.31 grams of carbon times 1 mole, 12.01 grams of carbon. I'm using the atomic mass of carbon. I'm gonna keep us that. For hydrogen, 5.14, 5.14 grams of hydrogen times 1 mole of hydrogen, 0.1 grams of hydrogen, atomic mass of hydrogen, 10.02, 10.21, sorry, 10.21 grams of nitrogen, 1 mole of nitrogen over 14.01 grams of nitrogen. And lastly, oxygen, 23, this is 23.33, so it's 23 grams of oxygen times. Let me just use 16.00. With this, we find the number of moles of each element in a compound. We need to find the number of moles of each element in a compound, 61.31 divided by 12.01. This is 5.10. And 5.0, no, 5.14 divided by 1.01, get 5.09 to two significant figures. And then 10.21 divided by 14, get 0. This is 0.73. These are moles. By the way, these are moles. All of them here are moles. Moles. These are moles. And lastly here, 23.33 divided by 16, 1.45 moles. In empirical formula determination, you need to find the number of moles of each element in the compound. Once you determine the number of moles of each element, you divide by the smallest number of moles. Divide by the smallest number of moles. All right. Doesn't really matter which one is the smallest. It doesn't really. It's not like always the first element. What's what I'm trying to say. You look at which one is the smallest. Let's go back to the example I do have here and say, what is the smallest number? I see it is 0.73. So this is our smallest number here. We divide by itself, we end up with what? We end up with 1. So if I divide by 0.73, so if I have here 5.09 divided by 0.7, I get 6.97. 6.99, so here is 6.99 and 1.4. 0.45 divided by 0.73. I get 1.918 or 99. This is 99. I'm just saying 99 just to make sure. So I've divided by the smallest number. And if I write that, the carbon, hydrogen, nitrogen, and oxygen. So carbon, hydrogen, nitrogen, and oxygen. If I plug in the numbers, I have here 6.99, 6.97, 6.99, 6.97. Here is 1, and for oxygen is 1.99, 1.99, 1.99. This is approximately like 672. So this is 6. 2 like that. Just round off to make it a whole number. So if you are given the mass percent, assume you have those as grams, and then you add the you add them to give you 100%. All right. So that is how I'll do. That's what we did for the empirical formula for pounds. You end up with that. Similar way, so always assume to be 100% or 100 grams of that. That is the what? The number of molecules of carbon, molecules of hydrogen, nitrogen, and oxygen. Where you're wondering where these numbers came from, these numbers are just atomic masses of each element in the compound. Carbon is 12 from the periodic table, nitrogen 14.0, 1 16.00, sometimes 15.99. It depends on which periodic table you're using. The point here is you need to convert the masses to what? Masses to number of atoms. You look at now the atoms and say which one is the smallest. If I look at this is the smallest, you divide by the smallest, and that is where we get all this. How did we move from here to here? Is by dividing it by the smallest. So the criteria by which you pick which number you are going to divide by is the value you have in terms of the smallest. Does not mean always the third one. The smallest can be for the first element, the smallest can be for the last element. So this is the subscript for the empirical formula, Before we look at the molecular formula, in very rare occasion, and please be careful on how you round off. In very rare occasion, you may end up with something like A, and then once you divide by the smallest and B, for example, like that, and I have 1.5. I divided by, the smallest number. This is just an hypothetical chemical formula for a compound. I divided by the smallest, and there is still a fraction. Yet empirical formula should be whole number. How do I make it a whole number? You multiply across pi 2, pi 2. There is 1 there, and the empirical formula for this is A 2 and then P3. So it's not always that you round off when you have exactly 1 or 0.5. If you have exactly 0.5 upon dividing it by The smallest number of atoms is you can multiply by 2 across to make it what? To make it a whole number. Some situation you may end up with that. Now, in relation to empirical formula, molecular formula is given by empirical formula times n, empirical formula times n, where n is an integer which cannot be 0. It can be 1, it can be 2, it can be 3, it can be 4, it can be any number. It has to be a whole number. It cannot be fraction, it cannot be 0 either. If you multiply by 0, it's going to be 0. How to get the empirical molecular formula is first, you have to know the empirical formula and the value for n, where n is determined from this. You'll always be given the molar mass. You'll always be given the molar mass and always in grams per mole, all right, over E empirical formula mass. This stands for empirical formula mass. This is simply molar mass of empirical it is the molar mass of empirical formula. To get the n value in determining the molecular formula, n is determined from the molar mass, which is always given. You'll always be given. I've seen for most problems, you'll always be given the molar mass of a compound. And remember, this will also be grams per mole. Grams per mole at the top and grams per mole at the bottom will cancel out and you'll remain with a whole number. That whole number now will be the subscript, and then you open the parentheses to get the molecular formula. Maybe solving one example will help you out. The multiple we are talking about here is we find the empirical formula. If you are given, then you need to move on from determination. If you are given the empirical formula, but if not, you need to determine the empirical formula. And then from the empirical formula, you find the molecular formula. So how do we do that? The empirical formula for a compound was found to be, this is the empirical formula, CH. It has a molar mass of 78 grams per mole. This molar mass is, look at the whiteboard. Look at my whiteboard. This molar mass is always, this is what I was saying, it's always given. At the top is the molar mass. What is this molecular formula? If you look at this is the empirical formula. That means you have to find the molar mass of this so that it will be your denominator, empirical formula mass. Empirical formula mass is the molar mass of empirical formula. I have the empirical formula here, so I need to find the molar mass or formula mass. One carbon, use the periodic table. One hydrogen, use the periodic table. You add that will give you the empirical formula. The point here is, this is the equation. Look at the question. What is the molecular formula? The equation you will need to use is on the whiteboard. Empirical formula, which is what we have here, And then the n here, which we need to find from this equation, Once we know the n, we open the parentheses and you have yourself the molecular formula. Look at the solution. So what we are doing here is we are finding the, all right, we are finding the molar mass of umbilical formula or umbilical formula mass. There is one carbon, the other here is using whole number. Instead, you may use 12.01 times one carbon, then you add for one hydrogen. This is the molar mass of umbilical. It will be our denominator to get the n. So here is a whole multiple. This is our n now here. You see this 6? This is the molar mass, and the whiteboard, look at the whiteboard, always given at the top is the atomic mass, molar mass of the compound divided by empirical formula mass. We have ourselves the 6. You will not write this. Look at this. I don't want you to leave it as CH and then you put parentheses like this, and then you say, I thought that is the equation. You need to open the parentheses and make it our own number 6. 6. Sometimes you may be asked, identify the compound. This look like it's benzene. So that's how you find the the molecular formula. It is a simple concept that you need to practice. I know at the end of the chapter, couple of problems on empirical molecular formula, all right? That will help you in understanding empirical formula. Any question on molecular and empirical formula? All right. Well, I want to just get fast forward to quantitative analysis. Forget about the combustion analysis. I want to get to quantitative information on balanced equation. Remember balanced equation. From the balanced equation, what information do we get? From the word quantitative, it comes from the word quantity, how much. That means you have to quantify, you have to account how much is produced or given when two reagent or when a chemical reaction is carried out. The coefficient in the balanced equation, we looked at balancing the equation earlier on. Please revisit that. Example on the formation of H2O, liquid H2O from hydrogen gas and nitrogen gas, Recall the coefficient. If there is no number in front of a reagent, it is understood to be 1. You do not interpret a chemical equation, a balanced chemical equation, by saying 2 grams react with 1 gram to produce 2 grams. Or it is not like mass that 1 plus 1 equals to 2. No, you don't interpret it that way. Always in mass, we know 1 plus 2 or 2 plus 1 equals to 3, but here is 1 plus, or you read as 2 molecules react with 1 molecule to produce 2 molecules, or whatever you are dealing with. We will see this later on when it comes to the stoichiometry, mass to mass, moles to moles. That's how we use the coefficient in the balanced equation to show the quantities of the reagents and the product. It shows the relative amount of the product and the reagent. relative number of molecules of the reactants and products, you know where products are. We can use now the coefficient in the balanced equation to relate to what? To mass. We can convert the number of moles produced in a chemical reaction to mass. And there are, all right, there are several power 3 stoichiometric calculations which I can break it down as mole to mole. That means you are converting from mole to mole. There is a mole to mass or mass. Maybe I should use an arrow to make it straightforward. I should say converting from mole to mole, converting from mole to mass, which is the same as mass to moles. It's the same as mass to moles. There is mass to mass, which is the longest one, mass to mass. All right, mass to mass. And all of them are anchored on, or they are anchored on the balanced equation, If I look at what I see here on the PowerPoint slide, it falls under category 3 on stoichiometric calculation. It falls under category 3. That means you are starting from the first one here, you are starting from moles and then you end up with moles. That means here I have moles of A and I'm looking for moles of B. Here, moles of A, B. We can also have here mass of A and then mass of B, like that, moving from A to B. So the second one is you are given moles of A, you have to find the mass of B, and so forth. So here you are given the mass of reagent A, and you are asked to find the grams or mass of reagent B consumed or reagent or product C produced in a chemical reaction. There are multiple steps, step number 1, step number 2, step number 3. You need to go through this roadmap. There is no shortcut, by the way. There is no shortcut in mass to mass calculation. You need to use the molar mass of A to convert to moles of A, then the coefficient of the balanced equation. Remember balancing the equation? Yes. You'll be lucky if you are given balanced equation, but if not, you may be required to balance the equation. And then use the mole ratio to find the moles of B, use molar mass of B to move from there. Then you convert to grams of B, Mole ratio here, it's just a conversion. You know, when we say mole ratio, if I use what let me use this example here, hydrogen gas reacting with oxygen gas to produce liquid H2O. What does the mole ratio mean? This was liquid, by the way. This was liquid. If I have here, look, mole ratio 2, and then there is 1 there. This is what we call mole ratio. You read this as 2 to 1 to 2. It's not equals to, you do not write equals to. Here are our mole ratio, the ratio which is interpreted as for every 1 mole of oxygen consumed, 2 moles of 2 moles of hydrogen gas are consumed, for every 1 mole of oxygen consumed, 2 moles of liquid H2O are produced. For every 2 moles of hydrogen gas consumed, 2 moles of liquid H2O are produced. That's what is meant by mole ratio, And it's basically the coefficient in the balanced equation. It comes from the what? Coefficient in the balanced equation. If you have mole to mole, it is pretty straightforward. But if you are not given, then you need to balance the equation and take it from there. This is an equation where glucose is burned, consumed to produce oxygen and liquid H2O. The mole ratio here, let me just annot this here. See here, this is 1 to 6 to 6 to 6. That is how you read this equation. Now, how many grams of water can be produced from 1.00 grams of glucose? And 3 significant figures, the fact that we have 1.00, 3 significant. So here is our forecast. The glucose here and liquid H2O here. This is where we need to zoom in. The mole ratio is 1 to 6. 1 to 6. It does not mean, how you interpret the equation, it does not mean 1 gram will produce 6 grams. No, you don't read like that. You don't read like that. I can move on from, changing. If you look at the roadmap, you need to change grams of glucose, which is C6H12O6. All right. Using the molar mass of glucose, here, all right, is 180 H12. This is 12O6, 1 mole of I've used the molar mass. This is the molar mass of glucose. This is the molar mass of glucose. You see on the PowerPoint slide, we are using the molar mass of glucose. And then the mole ratio. Mole ratio here is 1. You need to know which one. Since I want to cancel out, if I want to cancel out moles of glucose here, that means glucose will be at the bottom because of space. Let me just put the numbers. This is the moles or coefficient, or just mole ratio. Since I want to cancel out moles of glucose, the moles of glucose will be what? Will be at the bottom. This is glucose, this is H2O. So here is 1 what? 1 for every 1 mole of C6H12O6, 6 moles of H2O. You need to know how you set up your problem from here, you start off with what you are given so that you reconcile the units. You see here, from grams to moles of A, from grams of glucose to moles of glucose, we use its molar mass, and this is how I set it up. So if I cancel this, I'll remain with moles of H2O. But the question is, grams of H2O, how many grams of H2O? So the last conversion factor here is, we are looking for what? Grams of H2O. And I want to, look at this, I want to cancel moles of H2O. So moles of H2O here, moles of H2O. From the molar mass of H2O, it turns out that 18.02, I'm getting this number from the periodic table, no, using the periodic table. If you're not given, you will have to do that. Molar mass of H2O, this is what I'll put in. This is going to be 1 mole. The last conversion. The green I do have here, look at the roadmap, molar what? More or coefficient in the balanced equation. This is the coefficient in the balanced equation. Up to this point, we have moles of B, which is H2O in this case. Use the molar mass of H2O to get the grams of B. So molar mass of H2O, 18.02, and canceling moles of H2O with the moles of H2O there, we remain with grams of H2O, grams of H2O. That gives you the final answer. You can just multiply everything you have at the top, divide by everything at the bottom, and that will give you the correct answer for grams of H2O. Some people, they might do step by step. So if I cancel that, let me just clear that, make sure you can see, clear all drawings so that we can see this. There is 1 grams of glucose. You can solve one problem or one step at a time, or you can write the way I did. This is used to find the moles of glucose. 180 is the molar mass of glucose. You may be given, or you'll be required to use the periodic table. Then the mole ratio, this is the mole ratio between H2O, that problem, and the glucose. Cancel out the way you cancel using mole ratio. And lastly, using the molar mass of H2O, this is the grams of H2O that will be produced when 1 gram of glucose is consumed. Remember the rule of significant figures, because we had 3 significant figures in 1.00 given in the first problem. We also need to record our final answer with the 3 significant figures. Any question on this mass to mass?
On the last conversion on your PowerPoint, it's supposed to be 18.02 or 180? I think 180 is
the last. Oh yeah, this will be 18. Yes, this will be 18. Not 180. Sorry about that. This should be 18. Thank you. This should be 18 because molar mass of H2O shouldn't be 180. Okay, it should be 18.0 stable. I'll fix that. Thank you. Any other question? Somebody, Jason? Yeah, you are right. Yeah, somebody brought to my attention. Yes, it is H2O is 18.0 or 18.02. Just make sure you use the correct molar mass. What I find it the longest and involving multiple conversion factors is mass to mass. For mole to mole, it is pretty straightforward. You can handle that. It's just moles of A, moles of B, and you have yourself the answer. There is heat, which I will leave to thermochemistry, chapter 5, how heat is also factored in. We will also look at that in details in chapter 5 when we look at the thermochemistry reaction which produces the heat. Reaction which produces the heat. All right, any other question? Real quick, let me just cover the limiting reagent. It does not mean limiting reagent. In every reaction, there is limiting reactant and excess reactant. Let me just use this abbreviation. It does not mean that a reagent or all reactant will be consumed at the same time in a chemical reaction. Some reagent may run out before the other one is completely consumed. The one which runs out fast in a chemical reaction is called the limiting reagent. It limits amount of the desired product. Hence the word limit, to limit amount. How I look at this is, somebody might think the reactant which is present in small amount is always the limiting reagent. No, that is not the case. Sometimes excess reagent is present in small amount. A sure way of identifying, determining the limiting reactant is to do the calculation and see which one gives you less amount of the desired product using mass to mass or mole to mole. I can define this as a reagent that produce or yield less amount of what amount of. So you have to do the calculation and see which ones gives you less amount of the desired product using the mass to mass calculation we just went through, and that will give you the limiting reagent. The other one, of course, will be the excess reagent. Excess reagent. So sometimes you may be given a visual diagram and ask which one is the limiting reagent, which one is the excess reagent. If I look at this, hydrogen gas is rather oxygen gas is the limiting, is the excess reagent. Nitrogen, the white sphere, I don't see any white sphere here, but if you look at the red sphere, there is something remaining. You see this? So this is oxygen. You can tell oxygen is the excess reagent. The white one here represents hydrogen. I don't see any hydrogen left after the reaction. This is the limiting reagent. It runs out. That's a conceptual problem. It's a concept. So oxygen. Suppose now you are given a problem. How are you going to determine? You have to do the stoichiometry, the quantitative relationship between product and reagent, and see which one gives you less amount of the desired product. I will solve this problem. Let's solve this and see how far we will go in terms of limiting reagent, excess reagent. Remember, all right, remember a reagent which produce less amount of the desired product is the limiting reagent. At this point, we don't know which one is the limiting reagent. We don't know which one is the excess reagent. We don't know how much will be left for excess reagent. You have to do the mass. So at the outset, you need to know the molar masses of your or atomic masses of your elements or compounds. In this case, zinc reacts with, all right, zinc react with silver nitrate to produce silver and zinc nitrate. Mole ratio here is 1, all right? You have to understand that mole ratio here is 1 to 2 to 2 to 1. Which one is the limiting reagent? This is how you will proceed, that if zinc is the limiting reagent, you write this is the limiting reagent. How much of silver will be produced? How much of silver will be produced? We have 2.00 grams of zinc times, now we are using the what? We are using the mole ratio. Remember stoichiometry, mole ratio between zinc and silver. For every 1 mole of zinc, 2 moles of what? 2 moles of silver are produced. Zinc and zinc will go, no, we just first of all use this. Sorry about that, I'm just plugging in. It's not going to work. You have to change the given grams to moles using the molar mass of zinc, 65.39. I'm using atomic mass of zinc to find the number of moles of zinc. Up to this point, I have determined the number of moles of zinc in 2 grams. Then the mole ratio between zinc and silver, for every 1 mole of zinc, 2 moles of silver are produced, moles of silver, Ag. Moles and moles will go. Last conversion factor is 1 mole. This is the molar mass of silver, and silver is 107 point what? 87 grams of silver, Ag. Let's see how much will be produced. This conversion factor I do have there. Let's see, grams of silver, 2 times 2 times 107.87 divided by 65.39. I see 6.59 grams of Ag of silver will be produced. Then you come and say, if Ag, silver nitrate, is limiting reagent, how much of silver will be produced? In a similar way, we will, all right, we will just set up the equation 2.50 grams of silver nitrate AgNO3, give me 1 minute, times the molar mass of silver nitrate is 169.87 grams of silver nitrate, 1 mole of silver nitrate. Then the mole ratio for every 2 to 2. So 2 2, this is moles of silver, moles of silver nitrate. And then mass of silver is 107.871 mole of Ag. So that we cancel that. Let's see how much of that will be produced. 2.50 times 2 times 107.87 divided by 169.87. This is 1.5 9 grams of silver. So from this calculation, the one which gives less amount of the desired product is silver nitrate compared to the one we do have here, 6.9. The one which gives us less amount of the desired product is the limiting reagent. So which one is the limiting reagent? It is silver nitrate. And then the desired product, the product produced from the silver nitrate is 1.59, and that is the mass of the desired product. I want to stop here. We will pick up from here next time. So C and D, we will look at that next time. It is now 12:32, so for extending 1 minute. We will meet again next Tuesday. The exam will cover up to the limiting reagent concept, all right? Is there any question? I'm just gonna stop sharing my screen right now and take any question you may have. If there is no, I'll see you again next week. Thank you, have a great weekend. The class is dismissed.